Alright, hello Connor, or whoever else watches this video. I figured I'd just do kind of a walkthrough on my chess project, kind of where it's at, how it works, detail a couple of the shortcomings I have from what I originally set out to do. Um, I know nobody really likes to read documentation, myself included, so I figured I could also take this opportunity to do some of that in a video form. Um, I have no idea how long this video is going to be. I know a little bit about what I want to talk about, but kind of just going to talk and see where it goes. Might be 15 minutes, might be an hour. I don't really know. But first things first, I figured we could just kind of walk through the project, what happens when things happen, so to speak. So if we start, right at our public static void main entry method for a Java app. This opens this goofy little window here, which is a shocking amount of code for how little it does. Mostly just opens the browser, which you've probably experienced if you've tested this project at all. Why is that not showing up? Who knows? Anywho, so that also does a couple other things when you start the program. It starts the Spring application. So we're using Java Spring Boot, which is kind of just an easy web hosting framework. Handles a lot of the complicated stuff for me because I don't want to spend my time writing boilerplate code. So this is hosting an HTTP server whenever you run it that allows it to kind of handle API requests completely locally, right? So your computer is serving as both the server and the client, and that lets us interact through a web browser like this, which is really convenient. Lets us use HTML and CSS and JavaScript instead of writing everything by hand using Java Swing, which is how we open that goofy little window. Swing is not to be confused with Spring, but this is a really old graphics framework. I don't really like it. Anywho, so the last thing that this entry method does is it resets the board, and so that takes us to the chessboard class, which does like 60% of the important stuff, I would say. Interesting thing about the chessboard is, well, one of the big changes that this project took from the last time I wrote a chess engine is that we use bit boards for all of our board positioning. So instead of using a traditional array where you have a bunch of different bytes on your board that represent different pieces, right? So you could have, I don't know, maybe a 6 is a king and a 5 is a queen, or whatever it may be, and you just have numbers on a board like that. It works, but it's really inefficient because the way that Java especially handles arrays just isn't quite as nice as the way it handles bitwise operations. So instead, for every various piece, we have a 64-bit number, which is just very conveniently long in Java. And anytime a bit is on, that means there is that specific piece there, and when it's off, there is not that specific piece there. And this allows us to use bitwise operations to manipulate pieces, which are really fast. There's just hardware implementations of all bitwise operations on modern CPUs, so everything happens incredibly quickly. So when we reset our board, if we go to the reset board method, we just very manually set all of these bit boards to their correct manipulations for each piece, right? So for example, the white pawns, we have 8 bits on, right, where the pawns should be. That's how we do that. Obviously, these numbers are in hexadecimal instead of binary, but if they were in binary, it would just be lots of zeros and then 8 ones and then some more zeros. Okay, so that resets the board. And then you're taken to this page, which all of this programming is done in Svelte for the front end because it's just a little bit more easy to use than like actual pure HTML and JavaScript. And actually, I might open this up in Visual Studio. We have all our pieces. This is just because these are the little Unicode characters of each piece. Very convenient to have those. We have our board, which is a separate representation of the board that we have back on the server side, so to speak. This one is an array representation, but that's okay because nothing's really being processed on the front end, the client. So we can be efficient. That's fine. We fetch the board. That's just an API request to API get board. That's just where I was hosting it. It's on the local host, obviously. So, and then down here we display the board. And yeah, as I mentioned, we're using Svelte to make this stuff easier. Okay, and then the user will move a piece. So whenever you click on a square, you can see on click, it'll ask a few things. It'll select square, or it'll handle move depending on whether it's the first one or the second one you select. If you select the square, it'll get available moves for that current square. So that API request is handled. We'll go back to Eclipse for this. If we go to our API controller, get moves for a square, we first convert the square selection to a bitboard representation. So it's just a 64-bit number with just the 1 bit turned on. Because again, everything on the server is handled in bitboards. And then it'll find all the moves that can be moved to from that square. So first we just generate like literally every possible move you can take, which is a little bit inefficient, but it happens fast enough that doesn't really matter. And actually we can take a look at that method. Why don't we? So first we check if it's the white turn. And we select opponent pieces and empty squares. Those are important because it kind of tells us where we can or can't move, right? If it's an empty square, we can move there. If it's opponent square, we can take there. Pawn moves, these are, we just check if there's empty squares in front of us. If there is, we can move. If it's, we also have the first double move. It's implemented separately. And then capturing diagonally. These are pretty straightforward. Knights are a little more interesting. Actually, at the beginning, in initialization, we generate all of the knight moves for each square. So we have this is an array, which is kind of the best way to do this. We have a 8x8 array, and for each point, we just calculate the knight moves for each point. This all happens in initialization. We only do it once the entire time, and then we have a bitboard for each square of where a knight could move from that square. And those knight moves are computed here. It's just the 8 places a knight can move from each square, and if it's off the board, it just gets ignored. Yeah, so as I said, this happens only once for each square at the beginning during initialization. And then we have sliding moves. These are all handled kind of together. Bishop, rooks, and queens. The sliding moves from each square. We again cast, do a lot of this during initialization. We cast rays from each square in each direction. So up, down, and left to right, and then each of the diagonals. We cast rays from each square in each direction, and add that to bitboards. So we have 8 arrays of bitboards. So each one of these arrays has 64 bitboards of how a piece can move in that direction from that square. all done, yeah, again, during initialization. And so then for each sliding piece, bishops, rooks, and queens, we allow it to cast rays in the direction it's allowed to cast them, right? So we have, let's go to generate sliding moves. So this method will be passed with booleans for whether this piece can move like a bishop and whether it can move like a rook. So a queen will have true in both of those places because it can move in both ways. And then you look at those computed bit boards, and effectively you try to slide until you can't slide anymore, is the idea here. So you move one square. If it's empty or an opponent piece, you're allowed to move there. If it's empty, you can keep moving. And then we add all of those potential moves to our possible moves. And finally, kings, we again pre-compute every possible king move from each square at the beginning. So again, an array of 64-bit boards of places you're allowed to move from each square. And then we check if they're legal every time we call generate moves. So that's what this method does. It comes back to the API controller. We first generate all moves, and then we return all of the moves for the selected piece, right? So the user selects a square, we generate all moves, and then we return the ones that that particular piece can take. Okay, so that's how we display the red tiles there for any given piece. And then you select your move, right? So what does that do? That will call handle move, and it puts a post request to the API to make that particular move that contains some body that has the data of the move. It's kind of funny. We'll throw back to the homework assignment I was doing earlier. Anywho, so yeah, that sends that post request make move, which calls board.perform move with all of the content of that request. So perform move, that's down here. A lot of bitwise operations. So we have the from square and the to square on that move. First thing we do is we switch whose turn it is, because a move has been performed. So if it was white's turn, it's not black's turn, or vice versa. And then depending on the piece of the move, we adjust the bit boards. So we remove the from square from the relevant bit board, and we add the to square to the relevant bit board. So whichever piece it is, we adjust the correct bit boards. And then if it's a white piece, we remove, so yeah, the positive pieces are all white, negative pieces are all black. If it's a white piece, we remove it from the white piece bit board, and then add its new square to the bit board, and then we remove that particular square from every black piece's bit board in case it captured. We don't necessarily know what it captured, but it may have captured something. If it didn't capture anything, then all of the relevant squares on all these bit boards will just be off anyway, and so they'll stay off. And then obviously the opposite things if we're moving a black piece. That's how we perform a move. And that's what I was saying about bitwise operations. They're all really, really fast. So sometimes the code ends up being a little more verbose. Obviously, this is kind of a lot of code just to perform a move. But every single thing that's happening here is incredibly quickly. This case switch, right? It's super fast. All of these operations, I mean, as I said, they all have hardware implementations, so they run really fast. Okay, so that's how the player can move. But what's probably much more interesting is how the computer moves. So let's look at that. You click get computer move. What exactly happens? Oh, I was doing some debugging, so this is only thinking 2 moves ahead right now. But I'll switch that and make it a little more interesting. Yeah, you can see my note to myself. Let's make that 10. And then we will just restart real quick. And all right, so you can see it's printing some stuff at the console. I was doing a lot of debugging earlier, so We're still running that, but there it is. So it evaluated how many boards, considered how many game states, total of 8 moves ahead, and it moved its knight out. It's not a bad move. But what exactly just happened? So again, it all starts on the front end, but it's not much happening here. Get computer move. It prints a couple things to the console, and then it sends a request to computer move that contains the time that you've told it to take. So that gets handled again by the API controller. Computer move, and it will perform the move that the move searcher finds. So move searcher is this class over here. Let's collapse those comments, make this a little more legible. So find best move, it's passed the current board state, which again it's just immediately the pulled board state, and it's also told how long it should take. It gets the current time so that it knows what to compare to, and we do that calling current time millis, which is probably not the best way you could do this, because current time millis is liable to things like leap seconds. It's based only on your system time, not on any sort of absolute time. But the alternative would be to call nanotime, which is slower. It takes I don't know exactly how long, but a little bit longer. So we don't want to do that. You could also just change your system's time while it's running, and it would kind of goof it up, but whatever. We start with a depth of 1. So this is doing what's called iterative deepening, where because I want to set a limit on how long it can take, I need to be able to stop it kind of at any point. And so if you did a traditional depth first search, which we kind of have to do to use alpha beta pruning, which drastically reduces how many boards you have to evaluate. If you did a depth first search, you can imagine you're exploring your tree, and if you stop at any given time, you may just have not at all analyzed half of your tree. So if the best move is somewhere in that other half, you would never find it. So what iterative deepening allows us to do is start by only looking like 1 move ahead, evaluate all of those, go 2 ahead, and so we're still doing depth first at each depth, but we always have something to fall back on, right? So if we get stopped halfway through our depth of 8, we just use our best move that we found so far, which, looking at depth 7, would still be potentially the best move. So that's what iterative deepening allows us to do. We start at depth 1, and we keep increasing our depth until we get to max depth. And then within each depth, we start a new iterative deepening task. And so what that is, that's this class here. This is where some of the more complicated things happen. So we start a new task, pass all the parameters, and then whenever we compute, we first check if our time limit's been exceeded. If it has, we just stop. Otherwise, we call this alpha beta pruning algorithm, which is supposed to find the best move. First, we take a Zobrist hash of the board, and so this allows us to use a transposition table to see if we've evaluated this board already. So this takes all of the current data from the board, where each piece is. I haven't actually implemented castling yet, but eventually it will take into account who's allowed to castle. Again, also haven't implemented en passant, but if I had, it would look at whether you can capture en passant. Those things aren't reflected in the current piece state on the board, so we have to do them separately. And also whose turn it is, which again isn't necessarily reflected in the pieces on the board. So all of that's kind of XORed together into one 64-bit number. And so there is potentially an issue where 2 boards might evaluate to the same state, but this number is randomized enough that it shouldn't really be an issue. Yeah, we use a hash here that it's very unlikely, and this 64-bit number can represent I don't know off the top of my head, like 9 quintillion different numbers, so it's unlikely any 2 boards will be the same. Okay, so we compute that hash, we look in our lookup table, and if it already exists in the lookup table, we just take the value from there that reflects its current board. Otherwise, we compute it anew. We also do reflect alpha and beta values in this board, in this lookup table, that is, which could drastically reduce our search time, even if we don't have an exact value. Assuming we have nothing from there, though, we move on. We generate all moves that can be made. If there are no moves that can be made, currently, I just assume that all of your pieces are gone, in which case it's bad for whichever player can't move, and so that's reflected here. This could also mean a stalemate, which I don't currently check for, but for now we just assume all our pieces are gone. And then we start a sort of counter, and we assume to start that the board is as bad as it could possibly be for this player. Okay, and then for each move, we try making that move. So we create a new board that's based on this board with a particular move made. That's what this constructor does. It copies the board, and then it performs a move on it. And then immediately we start a new iterative deepening task on that board, which is just calling the same class again, right? That's the idea of this. This is a recursive analysis, right? This is currently changed to disable multi-threading because I was kind of experimenting if it was actually any faster. I think it is, but actually in the current state the code is not multi-threading. So yeah, we evaluate the new board with the move made, and if it's better than where we are, we update the move that got there to be the new best move. Otherwise, we do not. And then we look at our alpha beta pruning, and if that reveals that we no longer need to evaluate this branch, that is that alpha is greater than or equal to beta, we stop. So we break out of the for loop because there's no reason to keep doing this. Otherwise, we continue. And this is to do with the multi-threading. We would add our tasks to a task pool to evaluate simultaneously. So the idea here is until we reach our given depth, we do just keep evaluating the boards. But at a certain point, instead of continuing to go deeper, that's what this is at the beginning. So every time we call this, we reduce our depth by 1. And if the depth is 0, instead of computing every possible move, we just calculate the board value. So that happens somewhere down at the bottom of this, I think. Yeah, here it is. And again, I was doing some debugging on this, so normally this would not be commented out. So the first thing we do is we add up the value of each piece. This is pulling from board fields. So we have piece values. Pawns are worth 100. Knights are worth 320, bishops 330, rooks 500, queens 900, and kings, I think that's 200,000. You don't want your king to be taken, that would be bad. So we add the values for the white pieces, we subtract the values for the black pieces. Positive valuation is better for white. And that's well and good, but there's a little bit more to wanting to make a particular move. So to try and give some measure of positional advantage, I have these tables. I did not come up with these. I'm not that good at chess. I pulled them from this handy-dandy little kind of wiki guide here. So this is benefit that you get from having a particular piece in a particular location. So for every type of piece, you know, pawns, it's good to have them out towards the middle. Knights, you don't want them in a corner. Bishops, you don't want him in a corner, but it's not as bad to be in a corner as a knight, and so on and so forth. And so for each color and for each piece type, we look at where they are compared to these tables and add or subtract those values accordingly. And of course, we reverse the pawn table for black, because the pawns are moving in the opposite direction. Same thing for the king. There is this idea of a king endgame table where you want your king in a different place later in the game than you did earlier in the game. I haven't implemented this quite yet, as you can left a little note for myself, but that is something you would want to do. Okay, so that's that. We calculate the board value. Yeah, so that is that. Okay. And so that's how the computer makes a move. Where'd my board go? There it is. And that happens millions of times every time you tell the computer to move. But right now, the computer doesn't always make good moves. Like that. That was kind of a weird move. I don't really know why it did that. I can just take that knight. That was silly. So why is that happening? I have a couple ideas. This doesn't seem to be working, which is why it was commented out originally. And why might that be? Frankly, I have no idea. I would have thought this is kind of the easy part of the code. We are counting how many bits are on, and we are multiplying that by the value of that piece. That seems pretty straightforward. So yeah, frankly, I don't know. Somehow the value that it gets from that is being lost in this function, because if we just manually calculate board value on, like in our main method here, it is correct. It tells us the value of the board that I would expect to be the value of the board. So somehow that value isn't getting translated well in here. Even with a fairly minimal depth. And I swear I've looked at this code for hours and I have no idea why that is. Yeah, something's getting lost somewhere. Though, if I comment out, this is where it gets really weird. If I comment out that part of the board evaluation, it works like surprisingly much better. It does indeed move pieces to the middle of the board where I would expect it to. Yeah, that's weird. So if it reset, that makes sense. I guess I'm pushing that pawn at the beginning, but yeah, it'll bring its knights out, and it'll bring its pawns out, and all that, to avoid those piece penalties associated with having its pieces in bad places. Like the knight gets a -40 from being here and a +10 from getting here. So we can see if we restart this. Oh, sorry. I gotta completely stop the other one before I open a new one. Okay, well that's just straightforwardly exactly not what I expected to happen there. When I was testing this earlier, it did make the correct move. I think it's because I had it on a lower depth. Oh, yep. Gotta restart it. Obviously, that move it just made was very bad. There it is. Yeah, it pulls the knight out because that is the best thing to do. So clearly, at our larger depths, something's being lost somewhere that makes it kind of lose those valuations. And so I've tried all sorts of things. You could put like a penalty on the benefits it gets from later moves based on some sort of exponential function, so that evaluations 10 moves in the future are worth less than the same evaluation recently. Or, sorry, not recently, in like the next couple moves. It helped a little bit, didn't help too much. I'm kind of stuck between thinking that either my code isn't doing what I think it's doing, or that it is doing what I think it's doing, and just for some reason that logic is wrong. And it's probably somewhere in the middle, frankly, of the two. But nevertheless, something clearly isn't working. And so that's kind of where I'm at on this project. I've worked I don't even know how many hours trying to fix these problems, but without knowing what the problems are, it's quite difficult to approach. This project is, I don't know, like 3,000 lines of code total, so a tiny mistake even on one of those lines might cause drastic things to happen. Yeah. What haven't I covered that I wanted to cover? Honestly, I don't really know. There are all sorts of other classes that do various things, but it's all really just supporting what I've talked about. We've looked at some of them, we haven't looked at other ones. But I feel like I've covered most of my code. Okay.